All right. Well, hopefully this is working again. So, we left off talking about the fovea, and so how this is, the optic nerve is here, and then we'd have the fovea right above where the optic nerve leaves the eyeball, okay? Best spot with visual acuity, sharpness, clearness, all of that stuff. So, I saw somebody ask a question about the retina and if they had to know the makeups. Yes. So, if we zoom on over here, we have the whole eyeball, right? And then as we cruise back, we hit the retina wall. Right here is the very, like here's where the picture's reflecting. This is inside the retina wall. How vision works is it goes all the way to the very back of the retina. And this is where our rods, the blue things, and the red cones are, okay? They are going to start transducing the neural impulse, or to a neural impulse, or taking the light waves and transducing them. So it goes rods and cones, and then it'll go a little bit forward to the bipolar cells, and then it goes to the ganglion cells. You don't have to know the function of the ganglion or bipolar cells, okay? They're just in the retina. So rods and cones, bipolar cells, ganglion cells. The axons of the ganglion cells band together or bundle together, and they kind of like they twist together, and they create the optic nerve. Go, bud. They create the optic nerve, which will connect the eyeball to the brain. Now, the optic nerve, when it leaves the eye, right, it carries visual information from the eyeball to your brain. That's the connector piece. But if you remember, right, it doesn't go directly to the occipital lobe, right? It goes from the eyeball through the optic nerve. It'll cross the optic chiasm that we'll talk about here in a moment. And then it has to go to the thalamus. And then the thalamus has to redirect it to the occipital lobe. And then it has to go to the visual cortex, right, for processing. So the cool part is where your optic nerve leaves the eye, like in this drawings here, let me move my face over here, where the drawing goes, the red line is supposed to represent like the retina, right? Well, there's a gap right there where the optic nerve leaves the eye. The retina can't have tissue in that area. And what happens is it creates a blind spot. So I wish we could do this in class, but I can't because I don't have paper for you because I'm not with you. We could actually test the blind spot. I bet if you go online, you can find websites. Maybe I'll try to find one that you can test your blind spot out on. And so the ones I always use have like a plus sign on one side and a dot on the other. And you have to close one of your eyes and look at the plus sign. And if you bring the paper closer or further away very slowly, you'll hit the magic sweet spot where while you're staring at the plus sign, the dot has disappeared. It doesn't exist anymore. It's still there. It's just because you have gotten it on the spot in your retina where the optic nerve leaves, so there's no receptor cells there to pick up on it. So it can be called the blind spot or the optic disc. It's exactly the same thing. It's just where the nerve leaves the eyeball. So you have no receptor cells there. No retina is actually in that place. So there's nothing to process our vision. Now your brain does this weird thing where it cross paths. Your eyeballs crisscross in the middle in this thing called the optic chiasm. So what this does is it helps kind of like, well, not like what it does. It helps fuel things towards the opposite side of the brain, right? So we already have talked about how your left visual field goes into your right brain. Your right visual field goes to your left brain. We talked about it when we did split brain operation stuff. So this is just the actual mechanism in our head that allows this to happen. So here's this horrible visual pathway of everything that goes into detail of your eye. It's insane, right? If we could talk about light entering the eye, then the cornea bends it, then the iris shapes to let the pupil open or shrink to the correct size. The lens bends it, it reflects to the retina. Then the receptor cells, the rods and cones, transduce it. It goes to the bipolar cells, the ganglion cells. Ganglion cells, axons, create the neural impulse, or create the optic nerve, who then takes it to your brain. It crisscrosses, it goes to the thalamus. The thalamus says, hey, this is vision, go to the occipital lobe. And then the occipital lobe says, oh yeah, this is needing to go to the visual cortex. All this stuff happens every time you see something. It's super long-winded to talk about, even though it takes like not even a fraction of a second. That's like too long, right? It happens very quickly. So vision in the brain. We have something called feature detector cells, and these are specialized neurons in your occipital lobe that help you basically identify to some extent what you're seeing. So they respond to specific features, whether it be like angles, lines, edges, movements. Studies were done by David Hubble and Torsten Wiesel. And what they did was they used a cat's brain, and they showed what parts of their brain were reacting to certain types of lines, whether it be horizontal, vertical, or diagonal. And they realized that different parts of our occipital lobe, or different cells in our occipital lobe, light up when we see certain things. So the features of an object are all broken down. We have some features that pick up movement, some that pick up shape, some that picks up, a right angle versus a 45-degree angle. They're all different. So then, if we look at this, so feature detectors that would recognize different houses, and in different areas that feature different detectors that recognize faces. So, facial recognition, we talked about it being located on one side of the brain. This has nothing to do with it. We are saying that the reason you can tell faces apart in different shapes and notice differences in faces, like, oh, this shape's a little different, this angle's a little different, it's because of the different feature detectors you have in your eyes. Same with your house. You know what your house looks like, and you pick up on the different details and angles of the front facade of it because of your feature detector cells. Come on. Sorry, I'm struggling to use this right now. There we go. Okay, let's see if I can get this to work yet again without having problems. Okay, so parallel processing, I don't know where the video left off because just had some minor tech issues here. Parallel processing talks about how if I'm staring at like a robin flying off my deck, I can see the color of that bird, the motion, the form or the outline, and then the three-dimensional depth of it. But when I look at that robin, I see them all at the same time. I don't process them individually. I process these visual things all at once. So motion, form, depth, color, all those things in our brain are processed simultaneously. They are not separate things. And that's what parallel processing is, saying that these things are all being processed at the same time. They're all parallel to each other. They're all happening at the same moment. All right, so I will share the link for this blind sight video because it's super interesting. Blind sight refers to a person who has this odd ability. They are blind, they cannot see, but if you put them in this experiment type thing, or in the general, in the world, if that side of their face can't see anything, they can still perceive movement. And so in this experiment, they will have a man who is blind, but when they have a figure that moves one way in the screen, he can tell you if it moved up, down, left, right. He can tell you what direction this thing went, and it may be tied to the fact that maybe his feature detector cells, he might still have the movement one that's functioning in his brain, but he doesn't have any of the other ones that are for visual processing. But the movement one, for whatever reason, is still working, so he can see movement. He can't tell you what moved or what it was, but he can tell you what direction an object or something moved. So it's kind of an interesting one to watch, just the capabilities of the human brain. And then this video I'll post too about echolocation. People that are blind, whether they, well, typically these are people who are going to be like, this person had vision and then he went blind later in life. We talked about how your brain doesn't like dark, unused areas, this empty real estate principle type thing, where your brain will just move into those areas. And so for somebody who has gone blind, their visual cortex, instead of just being dark and unused and just wasted space, sometimes other areas will move in. So for this man, his it's kind of like his auditory cortex, not his ability to hear moved in there, but his ability to process sound. So he has an uncanny ability and lots of practice knowing how to use echolocation, so he can tell you where things are in space, even though he has no vision whatsoever. So another kind of cool one for the abilities of humans that I'll post on our classroom page. Now, color vision. If you look at this and I asked you what color is the dragon, you will probably say red. And I would actually tell you the dragon is actually anything but the color red. Because one of the ways, or not one of the ways, the way we see color is that the dragon is absorbing every other color except red. Red is the only color that is bouncing off the image, and when it bounces off, it goes and it shoots into our eyeballs, and that red wavelength is what is bouncing in to my retina, and I'm perceiving it as red. So any color you see on anything around you, it's because the color's actually, that wavelength, or the light wave is bouncing off of it. It's not being absorbed. If it was absorbed, we wouldn't see it. It's bouncing off and going into our eyeballs, and then we perceive the color red. So I always like this discussion because we can even talk about how, like, actually there's no such thing as color, right? Light waves don't have color. It's just the only reason anything has a color is because your brain perceives color to be a thing. It's how we understand the world around us and how our brain experiences the world. It's not because things actually have color, though. It's all in our brains. So color vision theories, the two major theories. First one is the trichromatic theory, also called the Young-Helmholtz theory. Okay, so both names apply for this one. Trichromatic is just kind of easier to remember because tri means three, and you should know red, blue, green. I'll tell you right now, step out of the art world. This is not art class we're in right now, and it's not going to work well if you try to keep doing that. So red, blue, green are the main colors. That would say we have 3 cones in our eyes, red, blue, and green. And different combinations of these will make all 7 million colors that we can see. It's great in principle, but the problem is it doesn't explain things like after images that we'll look out and color blindness. So color blindness, this is probably a thing you've seen in middle school when they do this in your science classes, right? And so people will say like the most common type of color blindness is red-green color blindness. Well, red-green, if this would be explained by trichromatic, that means you'd only be able to see like blue if the red and green are broken. So that doesn't make sense. Okay, color blindness too, when people think about it, sometimes people think, oh, they just can't see any colors. No, things are just muted very, very differently. Now, the other theory that fills in the blanks on this stuff, I did not make up these examples, so I'm going to blame apsychology.com, and by blame, I mean give them a shout out. They came up with this lovely example. Opponent processing theory says that we have pairings of colors and cones. So red and green go together like Christmas, yellow and blue go together like Hanukkah, black and white, just remember black and white, or you can look at Michael Jackson. But it says when one color is not working, the other one can't. So this idea like when something, I can't describe something as, well, it's like a reddish green color. Reddish green is like, what, brown? Same if it's like, oh, if it's a yellowish blue color, wouldn't that just be like green, right? Or blackish white, gray. You can't have these two colors working at the same time. It just doesn't work that way. All right. And then this is fun with after imaging. If you stare at this image and pause the video and then look into the white space, you'll see after effects. Okay, so this one, I'll leave this one up. This one's probably the most fun one, and we'll end this video for now here. But this one, if you stare at that white dot in the middle for a while, and then we'll flip over to a white screen, you're going to see a real life American flag. Because the opposite of yellow is blue, the opposite of black is white, and the opposite of green is red. So that would make sense on all of those. Then the last piece here, additive and subtractive color mixing. Think of it like lights. If I was at a play and I had a red light, a red light, and a blue light, and a green light, oh, sorry, I don't know how I said that, sorry, my brain's mush. And I put them all in one spot, it would make white, so that's additive color mixing. Remember, this is not art class. And then if I had the red, green, and blue, and I took them away and subtracted them, I'd be left with darkness. I'd be left with black. All right, so I hope this clarified some of the things. And yeah, there we go for I.